Hi, Andrew. How have you been?
Hello, I've been doing good.
We're going to be exploring applied math, specifically how it applies to epidemiology. Now, epidemiology is the study of the distribution and determinants of health-related states or events in a specified population. Basically, it's the study of the spread of disease. How do you think math applies to the spread of diseases?
I think of exponential growth, I guess.
We're going to learn about something called the SIR model. S stands for susceptibles. Susceptibles means everyone in the population that could potentially catch the disease. I stands for infected, aka those that caught it. Lastly, R stands for removed. So that includes those that have recovered, like some people euphemize it and call it recovered, but it also includes those that, died. People move from being susceptible to being infected to then being removed. As you can see here, there's three different curves. You can see all three graphs for S of t, I of t, and R of t. As the susceptible population decreases, as you can see on the blue graph, you can see how the infected population increases, it reciprocates that. And like you said, as infected populations increase and susceptibles decrease, you can see how the recovered is increasing. We represent in calculus differential equations with the following expressions. So it's like the rate at which the number of susceptible, infected, or removed people change. And what do you think would affect the rate at which the susceptible population, meaning just anyone really, how do you think it would change, realistically speaking?
Maybe it might change based on how many infected people are near the susceptible people.
So it's the relationship between how the susceptible people and infected people. It's the number that are there, and it has to do with the contact, right? Hand sanitizer, washing your hands, wear your mask. This would make the curve change like so. So do you notice the decreased contact rate? The contact rate for the one on the left is 3.30, while the one on the right is 0.80. And now let's consider vaccines. It moves susceptible populations directly to removed, since they would be effectively immune to this whole process. Multi-variable, we're gonna talk about multiple variables, right? So this here is how two independent variables affect one dependent variable. As the percent of not wearing masks increases and the percent of social gathering increases, you can see on the z-axis, which is, now it's turning 3D. We have a third axis now. The percent of being infected shoots up. Hello, thank you for joining me today. I already taught you about the basics. But today we're going to go a little bit deeper. We're going to go further into the SIR model. ds over dt is equal to negative beta times I times s. If you remember, we already talked about how the differential equation for susceptible populations, the rate of change for susceptible populations, is very much based on the contact rate between the infected and the susceptible. But there's also a proportionality constant. Now, if you look at di over dt, this beta times I times s goes from negative to positive. Because if you remember, the flow chart goes from susceptible to infected. So those that left the susceptible, that changed, that went to infected, it's now going to be added to it. So the slope is positive. Remember, the infected, it goes up and then back down. This downward slope is referring to gamma I times infected. And it's negative because this is those that are going from infected to recovered. Models are simplified, but we can modify or manipulate these models to include more of the confounding variables found in reality. So we call those SIR model variants. What if travel is taken into account? They spread it to each other, right?
Yeah.
Okay, what happens if we consider vital dynamics? Vital dynamics is a very fancy schmancy term for just if we consider births and deaths. Births go into the top one. Meanwhile, deaths, it says plus here, but the death value will be negative, like you said. And that's going to be involved in all of them because, if you're susceptible, infected, or removed, you can die. What if we consider vaccines? We're literally just going to be adding some constant value. The last one we're going to talk about is adding incubation period. We add a fourth category. It goes between S and I. We call it exposed. As you can see here, that when susceptibles come into contact with infected, they don't go to infected immediately. They're first exposed. They're incubating that disease. So they jump from here to here. After that, the number of people who go from exposed to infected, that isn't based on contact between S and I. It's just a progression over time. If we look at the epsilon value, you see there's another thing here. If you're susceptible, you can still catch the virus, like coronavirus, if you come in contact with an exposed person. But subtract it from ds over dt and add it to de over dt. So what happens if we combine all the variants? Because for every single variant, we were only talking about still a very small number of variables. But in reality, there's literally millions. Ways to mitigate mathematically. First is lowering S sub O. Oh, this is just referring to the initial susceptible population, which in general is everyone. The way you lower the number of susceptible, get vaccinated. As well, we're gonna reduce beta.
Wearing mask, practice good hygiene, wash your hands,
Yes.
social distancing.
Exactly. And then there's increasing gamma.
Have good medical treatment.
Yes. We can turn this into multivariable calculus by looking at a 3D graph. So what this study has done here is the way that the number of infected and the number of susceptibles is going to affect the rate at which people get infected. What they call alpha is what we've been calling gamma this whole time. Here, beta is equal to 0.3. What we call gamma is equal to 0.05 for this version. Here, beta is equal to 0.3, the same, but then what we call gamma is 0.1, larger, this value. And just conceptually, you can see why that is, because see how this dropped? That means that people are getting recovered more quickly, so that you don't have as big of a bump at once. More people are getting recovered, so the infected accumulation doesn't shoot up.
Sure. Yeah, so my background is in physics. Bringing together sort of good understanding of science and technology to a range of public policy questions. And a lot of those were around public health. Let's get going and see initial airflow flights going around the world. And for that run model I just showed you, the probability of a global pandemic is the key metric. So R naught in this method is beta, which is the rate at which infectious people are infecting susceptibles. Gamma is the rate at which people are being removed. So if someone is infectious today, what fraction of those people will not be infectious tomorrow? Eventually they recover or they die, in which case, either case, they're not infectious anymore. So R naught is just the ratio of those two. So that's a key number, right? If on average, an infectious person is infecting less than one new person, the epidemic, it's gonna die out. If on average they're infecting more than one person, then the epidemic will grow.
And upon learning about the basic reproductive number, I went straight to the drawing board and immediately found connections to what I'd already been teaching. Let's just take the basic equation for the differential of I of t and replace the s's and i's with those containing subscript 0, the values at time equals 0 before any outbreak. So when would we be sure that an outbreak doesn't occur? Well, when the rate of infections is negative, less than 0. And when we do some simplification, we get this relationship. Beta s sub 0 over theta is less than 1. This is the basic reproductive number that predicts disease spread, where less than 1 means it doesn't spread. This can apply to every facet of epidemiology and multivariable calculus we've covered today. For instance, the basic reproductive ratio can predict this hypothetical multiple regression model, where the two x and y axes would have steeper slopes with the z-axis if the basic reproductive numbers beta were high. Or, in these graphs, as theta increases, the basic reproductive number goes down, and thus supports the idea that infections would have subsided, like on the rightmost SIR graph. Ultimately, there's so much more math to explore in the realm of epidemiology. And if it brings us closer to deterring the possibility of another future pandemic, then it's more important than ever to start making these connections. Thanks for learning.